Hello, it's presentation about Ford-Fulkerson algorithm. It's algorithm to compute maximum flow from the source S to a sink T in the flow network. So here's a simple case with only one path from a source S to a sink T. As we can see, the maximum flow in this case is 5 because the lowest capacity in this path is 5. So when we set the flow to our graph, it's look like this. So first I want to show some notation which we will use to describe our algorithm. So the first thing is G of V and E. It's a network graph with set of vertices and the edges. C of U and V means the capacity of the edge from U to V, and F of U and V is flow from U to V, flow which we will set. So of course flow have to be lower or equal than C. GF is our residual network graph where we will update the current flow. CF is capacity in the residual network, so it's just a difference between the beginning capacity and the flow. So what is our input? The input is of course graph G with flow capacity. And we have to denote which node in this graph is the source node and to which node is the sink node. So that's it. And the output is just a real number which denotes the maximum flow from S to the T. So here's how our algorithm looks like. It's not very complicated. In the first step we just set every flow in every edge to be 0. Our algorithm will work while there will be any path from S to T which with residual capacity which will be greater than 0. So simply speaking, it will be working while there will be a possibility to make the flow bigger. So when we will find the path from S to T, then we have to find the minimum capacity in every edge of this path, actually residual capacity. So what we will get will be the capacity of the whole path. So then for every edge in that path we have to add the flow, or if the flow goes in other direction than the edge, then we have to subtract it. I will show it in the next example. So first a simple example, we have source S, we have sink T, we have the capacity in every edge, and the flow is set to be 0 everywhere. So it's our input, and the first thing which we have to do is we have to find the path. So let's take that one. And we find the minimum capacity, which is 1, and we set it to every edge in this path. Then the same thing for the other paths, and we have in here 3. So now we don't have any more paths in this graph, so the whole maximum flow from S to T is 4, which is a flow which comes from S or the flow which is going to T. They have to be the same. Okay, now example with the returned flow. So let's take that one. It's also the example of the worst case scenario of running this algorithm. So the first thing which we have to do is find the path. Let's take that one. Then we find the minimum capacity, which is 1. Then we add the flow. And we are looking for the other path. Let's take that one. We can do that because here we have flow which goes in the other direction. So the capacity of that edge is 1. It's not a 0. So the residual capacity can be equal to F when we are going in the other direction. So we update the flow. We have something like this. Then we look for another path. We update the flow. Another path. Update the flow. And it's the end. So we have also maximum flow equal to 4 in this case. There is the obvious question how to find the path. There is many ways to do that. I will show just one, which is the first search algorithm. We can see in here how it's working. It's example of recursive algorithm. We have to run it on the source S to find the path. So in the first step we label the current vertex in which we are to be discovered. Then if our vertex is already the sink, then we stop. If not, then for all edges from F to W, from V to W, to which we can go from V. So we do, if the vertex W is not labeled as discovered, then we run algorithm on it. If not, we are doing nothing with that. So here's example of the vertices to which we can go from V. We can go to V1 because it's not, the edge is not full. We can go to V2 because we can go in the other direction and there is not flow equal to 0, but we can't go to V3 because the flow is 0 and it's going in the other direction, and we can't go to V4 because it's full. So here's example of a graph in which we cannot find another path because, as you can see, the edges which are pointing to the T are both full. So as I said before, the sum of the flows from S have to be sum of the flows which are going to the T, and also the sum of flow in each vertex have to be equal to 0 because everything which will go to that vertex have to be sent from that vertex. So you can see it on that example. How fast is our algorithm? We have two loops in here. It's a while loop and a for loop. The worst case in the for loop is E because it's when our path is going through every edge in the graph. And the worst case from while is F because every time when we run the while we have to increase the flow minimum by 1, so we have to do F steps, maximum F steps. So our algorithm is order of E times F. Of course there is also the running time of the path finding algorithm, but in our case when we are using deep first search it's also E times F, so the whole running time is the same. Of course we can have the network with multiple sources and multiple things. Then our algorithm is not changing. Actually, the only thing which changes is that while loop. So our algorithm have to work until there won't be any path from any source to any sink. So while there exists path from any source to any sink T, we are just running this algorithm. You can find that path also using deep first search algorithm, but we have to run the algorithm on every source. So here's the example of multiple source and sinks graph. When we can use the Ford-Fulkerson algorithm in real life? Of course, everywhere we have network which looks like our graph. So the rivers are the good example. The black spots are the sources, green are the vertices, and the red points are the sinks. We can compute the maximum flow using the algorithm. Then when we will have more flow going from the sources than the maximum flow, then we will have flooding somewhere. And the other example is electricity. The sources are just the power stations, and the sinks are all our devices, electronic devices which we are using in our home. Okay, so that was the Ford-Fulkerson algorithm, and thanks for your attention.